Good afternoon, this is Schweitzer, and we're going to do a little video to talk about average atomic weights and isotopes. So, in this situation, first things first, let's look at an atom to make sure we're all sort of on the same page here. Alright, so we have three different atoms here, and this is actually the names of atoms, and of course these are all hydrogen. So, how do I know they're hydrogen? Well, we have the proton located right here, proton located here. Now we have a neutron here, and then we have a proton, and then we have two neutrons here. So in this case, what is the mass of these atoms? Well, this guy here is the mass number, which you should probably already know, but the mass number, all right, so the mass number is literally the mass of the atom, of a specific atom. So we could use kilograms for this particular mass, and you could find that conversion out, but it'd be super, super, super small. So in this case, we're going to use a unit called an AMU, so atomic mass unit, atomic mass unit. So this guy is going to have a mass number equaling just 1 AMU. This is the case because electron has essentially no mass, but it says protons have 1 AMU, and neutrons have 1 EMU. So this guy has a mass number, okay, mass number equaling 2 AMUs. All right, and this guy is going to have a mass number equaling 3 AMUs. 3 AMUs. So literally this guy here is 300 times more massive than this guy. So if I had a sample of 100 grams of this and the same number of atoms, but they happen to be tritium, it would weigh 300 grams. There is 3 times the mass. All right, so in this case, because all these guys have one proton, they're all hydrogen, and this is kind of an unusual looking thing here, but you can kind of imagine what they're referring to here. This is this number here that they had that I scribbled it out, but that's the mass number. This is the mass number here, and this is the mass number right there. So either way, these are called isotopes. So what is an isotope? Located here. Okay. These are atoms. So an isotope. All right. There's a lot of ways to think about it, but essentially they're the same element. All right. Now, when they're the same element, we're saying there's the same number of protons, but they have different mass, a different mass. Now, how do you go about getting a different mass? Well, the only thing that will give you a different mass is by having a different number of neutrons. So my neutrons are different. So the same number of protons, but different number of neutrons. And this is going to give me a different mass. So in this case, the masses could be wildly different. Now, for this is true. The tritium is 300% heavier. So we would make sure that, if we're weighing this out, if we're using these, which one have we got? The heavy one or the light one? So in this case, note that on Earth, okay, there's a natural abundance of isotopes in certain areas. Some areas are more massive, more abundant than others, but in general on Earth, you could probably consume that there would be a certain average of certain types pretty well distributed. But all right, so let's look at carbon, for example. All right, so in this situation, on Earth, now again, it's not on Earth, okay, we have carbon 12, we have carbon 13. Now, what is this notation meaning again? When we're looking at this, we're trying to describe a couple things about carbon. What do we think the 12 means? You might see a notation that might be a little bit different than what you might be normal to. For example, I don't know that I've ever seen the 3 located right here before. it looks a little different. Maybe this is from a different country. I got this picture from offline. But again, I should be able to resolve it with my brain what they think that 3 means. Okay? So in this case, what do we think the 12 means? What do we think the 13 means? Well, for carbon, if you look at the periodic table, carbon has, in this case, 6 protons. And what do we think the 12 means? The 12 likely means that's the number, the total mass. Okay? So in this case, they could have listed just the number of neutrons. That might have been a nice way to do it. But that's not what they chose to do with carbon or any atom. They just list the mass number. So this is meaning that there are 6 protons and there are 6 neutrons for a grand total of 12 as the mass number. Carbon 13 is going to be 6 protons and 7 neutrons for a grand total of 13. All right, so on Earth, okay, there is a natural abundance of carbon-12 at 99.9%. Okay, so if you grabbed, in this case, 1,000 carbon atoms, how many of them would be carbon-12? How many would be carbon-13? And the answer is there would be 999 carbon-12s, and there would be 1 carbon-13. Okay. Now again, you know, that may seem like, okay, why don't we just forget about the carbon-13? Well, that's okay. But typically speaking, the amount of atoms in, well, put it this way, 12 grams of carbon is 6.022 e to the 23rd, okay, particles, atoms. So you might think at this point, with this large number, we're going to have quite a few carbon-13s. Okay, now again, 99.9% of them are carbon-12, but there's some. Okay, so this is what we call sort of a mass isotopic average chart, you could call it. Okay, and my chart's not real, you know, I couldn't get this little thing to be smaller. It should just be just a squeak, you know, just a bitty little squeak, and almost all of them are there. Okay, what do we want to get from this chart? From this chart, we should realize that my average between these two is likely right about, just right there. It's not 12, because we got some of this. So my average is just barely above 12. Okay, even if you don't know the math, although most kids, if you offered them $50, they could come up with an average here, and they would get the answer. So in this case, if you look on the periodic table, you'll find the average is 12.01. So in this situation, okay, the average being that, okay, 12.0, what does that mean? That means that when I weigh out a whole bunch of these guys, okay, put them in a dish and I weigh them out, okay, my average weight would be 12.01. And that would be AMUs per atom. Now again, this is what we call an average. The average, okay, and you might see a couple different ways it's worded. It'll have it to molecular weight, or the molecular weight, or the average mass. Average mass, we'll go with that for today. You got to be able to discern the different vernaculars that people use. All right, so that's carbon. Now again, keep in mind, when I have an average here, what does that mean? Okay, well, it means that we have 6 protons. How many neutrons? All right. Well, neutrons, well, first of all, you can't have half a neutron. So to say we have 6.01 neutrons would be false. This is an average, so sometimes we have 6, sometimes we have 7. And the 6 looks like it's showing up a whole heck of a lot. All right, based on the average being really close to 12. So, average. All right, here's another example. Okay, this is zirconium. Okay, again, let's review. What are these numbers on here? Okay. Well, for a particular atom, each of these are representing a very specific atom. Okay. For zirconium-96, how many protons are there? How many neutrons are there? How many electrons are there? Take a moment, pause the video, and try it out. Okay, the answer here for zirconium, you look on the periodic table, and you'll find two numbers for zirconium. Now, zirconium is Zr. You'll find it, and it is 40. 40 is my number of protons. Now, when you glance up the periodic table, I know that there's two numbers up there. There I saw zirconium, this is my classroom, is zirconium, and the 40 is listed right here, and the other number is 91.2, 91. No, let me just rewrite that. It's 92.91. Got that right? One more time. 91.22. 91.22. All right, so finally got it. Okay. So what do those numbers mean? Well, first of all, the periodic table is listed by number of protons. So which one of those is protons? Think about that for 1 second. All right, well, if you look over at the one to the right or the one to the left, you'll notice that next to zirconium, or just go to the left, I like that one better here, is yttrium. And yttrium's got 39 here and 88.91. 88.91. All right, so in this situation, which again, the periodic table is ordered by number of protons. So therefore, this is my protons, and this is my average. Notice that the mass number is not even on there. All right, so what are these numbers? These numbers are for an individual atom telling us the number of protons. We got that from here. This is both. So 96 minus 40 is 56. So this particular atom has 56 neutrons. And the electrons are, well, they're not even listed here. So I don't even know how many electrons we have. All right. Can you estimate this average? Now, again, I've given it to you on Earth. Okay, now, again, you go to the moon, might be different average. Different planet, different average. But you should be realizing that your average is someplace in here, likely. It's not over here. The average is not here. Okay, the average is not over here. The average is likely someplace, probably in here. Okay, somewhere in this range. And when you look at on Earth, these are distributions on Earth that someone went out and actually collected. That was someone's job here. Someone got paid to collect zirconium atoms and analyze them in a lab. All right, so the average is 91.22. Does that kind of make sense? So they're saying it's right, just right about here. Yeah, it kind of makes sense. Okay, you should be able to look at a chart and discern, you know, what these numbers mean and what my general average might be. All right, here's another example. Okay, so lithium. Now, what are lithium's most common isotopes? All right, well, if you look at the average is, so is lithium, and it is 6.94. Now, again, we don't know a lot from the average. For example, you can go have a 0 score and a 100 score and average 50. Or you could have a 40, 48 and a 52, and you can average 50. So you don't exactly know what the exact isotopes are here that give you this average. You're never going to know that from this average. You could probably guess that 7 is a very common, but we don't know for sure, but likely this is typically what's happening. So lithium 7 is likely the most common isotope there is. So how would you know what the different isotopes are? You're never going to know. Okay, only way you know would be to literally go out and search for lithium and measure it. Or you go online and get someone else's data and use their data. So that's what I did. So I searched lithium and go online and see the various isotopes of lithium. And there might be a bunch of them. The source I found showed only 2 of them, lithium-7 and lithium-6. Okay? Only 2 of them. All right, so at that point, if you were to make your own chart here, we could go lithium-6 and lithium-7. Again, we want to know, what do these numbers mean? They're the mass numbers, right? I'm not using the average here because I can't have a mass number. The mass number has to be a whole number. That's kind of important. The average could be a whole number if you got lucky, but typically the average is a decimal. All right, so lithium-6 is going to be relatively small, and lithium-7 is going to be relatively large. Ends up being about 96% and about 4%. About that. That's, I think, what I got online. But again, only way you can get that is from actual data. Okay. All right. In the end, why do we really need the average atomic weight? All right, why is the average atomic weight on the periodic table not the mass number? Okay, so you don't, at this point, you may not know a whole lot about chemistry, okay? But one thing about chemistry, I'm going to just show you an example here, is let's just say we have H2 plus O2 yields H2O. And we balance things, and a lot of chemistry students have been balancing equations for years in younger grades. But there's a 2 that goes here, and a 2 that goes here, and a 1 that is there, but you just can't see it. So one thing you want to note about these things is that these guys are actually measuring actual number of atoms. That means I need 2 of these guys for every 1 of these guys, and I get 2 of those guys. Or I would, if I consume 4 of these, I would need 2 of those, and I would get 4 of these. So this actually is number of particles. Okay, number of particles is super important when running chemical reactions. So mass, okay, well, what does that mean? Well, mass is kind of useless to us. We really, because atoms are so small, we really only use mass as a means to count. Anytime on Earth, for people, you need to count something that's very small and there's lots of them, we weigh them. So we use mass to convert mass actually eventually into number of particles. And then we'll get there eventually. So, but how do you get that? Well, you need to know how much one particle weighs. How much does one unit weigh? Or what's the mass of one unit? So again, if I were to say that carbon is just 12 AMUs, okay, then when I took my mass and take the mass and of the carbon and just divide it by 12, well then I'm not going to get the right mass, the right number of particles, because it's not actually 12. Some of them are heavier. So what I do here is I take the mass, all right, and I divide it by the average. And because there are so many of them, the average works nicely. And this will give me my number of particles. So in the end, just foreshadowing some things coming down the line, is that why do we really need the average? Because eventually we're going to use it to get the number of particles. And of course, if I'm using hydrogen, if I used a mass number of 3, for hydrogen, okay, if I took the mass of the sample I'm using and divided by 3, well, that's 300 times more than the other hydrogens are. So some of them are close, some of them are much bigger difference. Okay, so why is the atomic weight on the periodic table and not the mass number? This is kind of an interesting little thought here. The mass number is only for a single atom. Now, on paper, we might be able to do something like we have here and show a single atom of carbon. But in reality, the number of particles that we are using is frustratingly large. So we really never deal with one atom, okay? We're dealing with lots of atoms and lots and lots and lots and lots and lots of atoms. You can't even possibly fathom how many atoms are in a single breath, okay? So invariably, if we're dealing with that many atoms, we're going to have isotopes mixed in. And the average is what really allows us to know the average of all those isotopes on Earth. So this is the average, okay, isotopic mass. It sounds kind of isotopic, sounds intelligent. It sounds like you're a scientist here or something. Average isotopic mass, but really it's just an average weight of all those on Earth that someone figured out. All right, so last thing we're looking at, and I've used a bunch of these already, is some of these symbols. And really, if I say, for example, got one more slide here, I believe, you know, molybdenum, you know, MO, and I go like this, you know, 96, okay? A couple things you got to be aware of. Okay, what do all these numbers mean? The mass number should be able to determine on any periodic table. This one's on top here. On my wall in my room, it's on the bottom. That's fine. You should be able to note whether you're talking about a mass number or if you're talking about an average. Okay. Okay, we got our symbol here, and we got the name. So various things, and then some periodic tables have lots of information here, but you should be able to discern what that actual, I would call this a model. This is really a modeling an atom, okay? What is it? It's got a certain number of protons, which is 42, and for this particular atom, you could actually get the number of neutrons. Those add up to 96. This is my average on Earth. We're going to stop there for today, and thank you very much.